Good afternoon, student. So welcome to the live session of the optimization. Welcome to the live session of the MOOC course on optimization methods for civil engineering. So today we'll discuss mainly whatever question I have received. So there are some queries from the student and that I will discuss. But before that, let me go through the lecture. So what we have gone through till now. So I've explained what is optimization here. I think right now you know what is optimization and where we can apply optimization methods. And then we also discuss classical optimization. So I said that so we have classical method as well as non-classical method. So we have discussed mainly classical optimization method so far. And in classical optimization method also we have discussed initially linear programming. So I discussed about linear problems. So where objective function and the constraints are linear in nature. And then we discuss mainly how you can solve a linear problem using Excel. So easily you can solve a linear problem using Excel solver, or I have also discussed how you can solve a linear problem using simplex method. So and then we discuss about nonlinear optimization method. So basically for a convex function, how you can bracket an optima using a bracketing algorithm. So that I have discussed. Suppose you have a single variable function and you would like to bracket the optima. So I have discussed those things in lecture 7. And then we applied region elimination technique to find out the exact optimal solution of the problem. So that we have discussed. And apart from that, I also discussed the gradient based method like your Newton-Raphson method. So that also you can apply for finding the optimal solution of a single variable function. Then I discuss about convex function because it's a very important characteristics of a function, that if you know that your function is a convex function or if your problem is a convex problem, so in that case, so what you can do basically, so you can apply classical optimization method for such problem. So you need not go for non-classical optimization method. So later in this particular course, so I will discuss about non-classical optimization methods such as genetic algorithm and particle swarm optimization and some other algorithms I will discuss. If your function is a convex function, so you need not go for such type of algorithm. So easily you can apply you can easily apply your classical optimization method for finding the optimal solution of this problem. So I have discussed how you can check whether your problem is a convex problem or a non-convex problem, or whether your function is a convex function or a non-convex function. So that I have discussed. And then I have discussed how you can actually find out the optimal solution of a multivariable function. So whatever region elimination technique or bracketing algorithm we have discussed, so that actually you can apply for a single variable function. But in case of multivariable function, how you will get the direction. So and based on that direction, actually you are doing some line search. So whatever method you have learned under region elimination technique or bracketing algorithm, so that you will apply. So multivariable function. So what you are doing basically, you are finding the direction. Now direction you can find out. Suppose I have discussed some your method like univariate method. That means we are going through one direction at a time. So univariate method, then steepest descent method, then Newton's method, and then conjugate direction method. So based on that, you can find out. Then I also discussed that which one is better for what type of function. Suppose I said that if your problem is a quadratic problem, that what algorithm you will use, that you will use mainly the Newton's method, because if you apply Newton's method, so in a single iteration of your of your line search method. So you will get the solution in case of Newton's method. So you need not apply other method. So therefore, based on what is your function, so you can apply or you can select your algorithm. Then I discuss about quadratic approximation. Suppose I say that if your function is a quadratic function, so in that case you can apply Newton's method. So what I can do, I can for non-quadratic function, I can approximate the function as a quadratic function, and then I can apply the Newton's method in an iterative way. And then I have discussed the constraint handling. So whatever I have discussed earlier, so it can only solve a problem without any constraint. Then I have discussed how you can handle a constraint. So penalty parameter approach I have discussed, so that you can apply for solving a constraint optimization problem. So there are different functions. There are different your penalty function that you can use for converting your constraint optimization problem to a unconstrained optimization problem. And once your problem is an unconstrained optimization problem, the algorithm we have discussed so far that you can apply for finding the solution of the problem. So this is so far we have discussed up to your lecture 15, and then now in next class we will start basically the non-classical optimization method, but here almost we have covered the classical optimization part. So now I have received some question. These are some clarification has been sought, so I will try to explain that one. So one is that in a multivariable optimization by Newton's method, so I said that you can apply Newton's method if your problem is a quadratic problem. In single iteration, you will get your solution, but you can also apply your Newton's method for non-quadratic function. Also, in that case, you need more number of iterations to get the solution. So his question is, in a multivariate optimization by Newton's method, how will we calculate the double differential matrix using Taylor series, not the direct differentiation? Does it make the process of calculation much more tedious? Okay, so what he is asking that in case of Newton's method, so you need to calculate the Hessian matrix. Okay, so you need to calculate the Hessian matrix. So Hessian matrix you need to calculate. So this is basically, suppose 2D function, I can say that this is del square f by del x squared, and this is del square f by del x del y. This is del square f by del x del y, and this is del square f by del y squared. Okay, so this is basically the this is the second derivative of this particular function. So this is a this is your Hessian matrix. And in case of Newton's method, so what you have to do, you have to calculate inverse of the Hessian matrix, and then you are calculating the direction. So this is the negative value, and this is the direction. So here what you have to do, you have to calculate the Hessian matrix. So the question is that how you can find out this Hessian matrix using numerical differentiation. So we call it numerical differentiation, not differentiation. So we'll try to calculate or we'll try to calculate this Hessian matrix using numerical differentiation. So here I would like to explain this thing. I have not discussed this thing. I think you know this is the Taylor series for single variable, that is f of x plus h. F of x plus h equal to fx plus h f dash x. Then h squared by factorial to f, this is the second derivative, and h cubed by factorial 3, this is the third derivative. So this is I'm writing f of x plus h. Similarly, I can also write f of x minus h. So in that case, this will be your negative sign, and this will be your negative sign. So now if I add these two equation, that is equation 1 and 2, so what I will get, I will get this particular equation. So I am also ignoring the higher order derivative. So here this is negative positive, and it will cancel out. Then first derivative will also cancel out. So you will have only the second derivative, and second derivative in that case I can calculate, which is f of x plus h minus twice f of x plus f of x minus h divided by h squared. Okay, so I can use this equation for finding the second derivative of a function numerically. Okay, so I will also discuss for multivariable function, but this is for single variable function. So you just see, when you are calculating the second derivative, so you need three function evaluation. That means you are evaluating function at x plus h, then at x and x minus h. So therefore, the computationally it will be much more expensive because you need three function evaluations for calculating the second derivative. So certainly the process of calculation will be much more tedious, but question is that when you are writing program, so if you can give the derivative value directly, then your program will be efficient. But many times we cannot actually calculate, or we cannot give the derivative value. So in that case, we'll calculate the derivative using numerical method. So here I have shown you that how you can calculate the derivative, first derivative. So this is the Taylor series. Okay, so if I ignore or if I basically if I consider the Taylor series up to the first derivative, so this is the truncated Taylor series, then from here I can actually approximate that first derivative is equal to f of x plus h minus f of x divided by h. So I am not writing the equality sign because this is an infinite series. So I am only considering up to the first derivative. So therefore, this will not be equal to this thing. So, but I am getting an approximated value of first derivative here. And I can say that this is approximately correct because if you are considering that h value sufficiently small, so in that case, what may happen? This will give you a reasonably correct result. So when I am calculating this equation using f of x plus h, so in that case, this is a forward differentiation. And similarly, if I write that f of x minus h, which is equal to f of x minus, so this will be now minus and this will be your minus. And if I only consider the truncated series, so I can approximate the first derivative like this, that first derivative at x, which is approximately equal to f of x minus h divided by h, and this is known as backward differentiation. And I can also go for your central differentiation. That means what I can do that if I subtract the second equation from the first equation, that means equation this is 1 minus equation 2. Okay, so 2 is subtracted from 1. So in that case, I will get this equation and this equation, and from here, this is also a derivative at x, and this is your central differentiation. So I can use one of that for calculating the first derivative. Now let us see for multivariable function. Suppose if you want to calculate, this is the Hessian matrix, and I need to calculate fxx. So fxx, which is nothing but this is del square f by del x square, and this is fxy, which is equal to del square f by del x del y, and fyy, which is equal to del square f by del y square. And anyway, so this is yx is nothing but fyx, which is equal to del square f by del y del x. Okay, so what I can do, this is the first derivative of this multivariable function. So here f of x plus delta x comma y minus f of x minus delta x y divided by twice delta x. So this is your fx and this is the fy. This is the first derivative. And second derivative at xy, so I can calculate that is f of x plus delta xy minus twice f of xy plus f of x minus delta xy divided by your delta x square. So this is your del square f by del x square. Similarly, I can write what is del square f by del y square. So this is your del square f by del y square. So I'm writing f of x y plus delta x minus twice f of xy plus f of x y minus delta x. So this is your second derivative del square f by del y square. Now this is your del square f by del x del y. So what I can do basically, so I can write this is fy x. So this is the first derivative I am taking at x plus delta x and y minus f of y x minus delta xy divided by twice delta x. So this is the first derivative. So what I'm doing here, I'm just I'm writing del square f by del x del y, which is equal to I'm writing del by del x, and this is del f by del y. Okay, so that way, so now you are taking the first derivative. So this is the first derivative, and then if I take the derivative at the first derivative at x plus delta x and y. So this is this equation, and this equation is coming from here. Okay, so from the first derivative one, and finally I'm getting f of x plus delta x y plus delta y minus f of x plus delta x and y minus delta x divided by twice delta y. And similarly, I can write f of fy x minus delta xy, and this is. And if I put these two, in this particular equation, and finally I'm getting this equation, and this is the second derivative. That means del square f by del x del y. So I'm getting this particular equation. So now using this, what I can do, I can calculate the Hessian matrix of any order. Okay, so Hessian matrix of any order I can actually calculate. So even if suppose I have more than two variables, so in that case Hessian matrix will be something like this. This is f of suppose if I say f of one, this is f of 1 2, and this is f of 1 n. Suppose f of 2 1, then f of 2 2, f of 2 n, like that. F of this is f of m1, then f of m2, then f of mm. Okay, so using this equation, I can calculate the Hessian matrix. I can calculate the Hessian matrix of any order. Okay, so but what we are doing here, so we are calculating this derivative using numerical methods. Okay, so question was that how we are calculating, and second question was whether it will be computationally intensive. Okay, so because it will be yes, so computational complexity will increase because we have to calculate function yeah, at different points basically, and based on that only we are calculating the derivative. I hope this is clear, so I can apply numerical methods for finding the derivative, second derivative of any order. I can do that. So there is another question. The question is when you put x2 value as -6, then f value should be 12. Am I right? So this is related to this particular slide. So this is related to this particular slide. So here I have given an example of solving an optimization problem, and this is the objective function, and objective function is a minimization type. So this is related to linear problem. So here, what I have done, that I have considered x2 as a basic variable x2, and then I have considered x2, x3, x2, x4, and x5. So x2, x4, and x5. So I have considered as a basic variable, and other variables are non-basic variable. So here, what we are doing, so I'm considering this as a pivoting element. So in that case, what I will do, coefficient of this particular variable will be 1, and for other it will be 0 and 0. Okay, so I have applied the row that row elimination method. So here what I'm doing, so I'm making this is 0, and this is your 0. And then here already x4, so here it is 1, and for others it is 0. So this is 0, and this is 0. And x5 also, this is 1, and here it is 0, and here it is 0. So what I'm doing, so now this is my non-basic variable. So x1 equal to x1, x3, and x6. So they are equal to 0, and I have been and my basic variable is x6, x2, x4, and x5. So in that case, what is happening? That x2 equal to 6. So I am getting this is x2 equal to 6. Then x4 equal to -4, and x5 equal to your 12. Okay. Now if I and from the last line, what I'm getting, the minus f equal to +12, or you can say that f equal to -12. Okay. So this is the solution of this particular problem. Whatever we got, that is not a feasible solution because I am getting negative values. Okay. Now question is that if I put -6, so if I put -6 in the objective function here, then f value will be your -12. Okay, so f value will be -12, not your +12. Okay, I hope this is clear. So from the last line itself, so I can find out the objective function value. So minus f equal to 12. So similarly, if I consider this as my pivoting element, and I can I can solve this problem. So in this case also, I am getting x2 equal to -6, x4 equal to 8, and x6 equal to 12. And in this case, from the last line, what I'm getting, minus f equal to -12, or I can say f equal to +12. So if I consider this particular element as a pivoting element, so in that case, you'll be getting f equal to 12. So I hope this is clear, and so this is related to this question. So there is another question. This question is why can't we solve a maximization problem using simplex method? Okay, so here in the example problem, what we have discussed, or I have discussed in the class, so this is a maximization problem. The question is that why I have converted this problem to a minimization problem. So here in this example problem, so what I have done, I have converted this problem to a minimization problem. And how I have converted? I have converted the this maximization problem to minimization problem by multiplying -1. So because this maximization of f, which is equal to minimization of minus of f, basically. Okay. Now question is that whether we can't solve this problem as a maximization problem. Yes, we can solve it. Okay, so it's not that you cannot solve this problem directly. Okay, then yeah. So there are some issue. So we are discussing this particular question. So here the question is that why can't we solve a maximization problem using simplex method? So as I said, so I can solve this problem as a maximization problem. So in that case, what will happen? My rule will be different. So right now, what we have done basically, suppose we have gone for minimum your coefficient, minimum coefficient here. Suppose I can, so in that case, my rule will be different. So in the objective function, so I have checked what is the minimum one. Suppose this is the minimum one, and that actually variable I have considered. But now rule will be different because I am solving a maximization problem. So because of this confusion, so what I have suggested that you learn the methods for minimization type problem, okay? And then if you have a maximization problem, you convert the maximization problem to a minimization type your problem, okay? So and then you apply whatever rule you have applied for a minimization type of problem. So it doesn't matter actually. So you can directly solve a maximization type problem. But I want that because the rules I have discussed, this is for a minimization type problem. So you convert the problem to a minimization type problem and then you solve the problem. So we can solve it, but because our rules were for minimization type problem, so we have converted this problem. Otherwise, you can directly solve this problem as a maximization type also. There is no issue. So I hope this is clear. And then in this particular question, there are some concern. So there are two questions. How did we get the value of constraint before A and L? So question is that before knowing A and L, how you will calculate the constraint? Then second one, how did you assign the value of the coefficient? So this is not coefficient, this is actually variable. So this is, I have discussed that this is here, I would like to minimize the material cost. Okay, so this is the objective function. And finally, I'm getting this particular optimization problem. So here, this is the objective function. So this is the objective function. And these are all constraints. So altogether, this is my optimization problem. It's a minimization type optimization problem. I have minimized this particular function. And at the same time, these are the constraints in order to withstand the tensile stress, that compression stress, and as well as the stress should be safe for bending and deflection, or minimize the deflection at C basically. So once you are solving, so you will get a solution like this. Now question is that how we can calculate this constraint before knowing this particular value of A, A1, A2, A3, and A4. So here I would like to tell you that L is not variable. So L is basically, this is the already defined. This L value is already defined. Suppose this is an example problem. Suppose L value is 3 meter. Okay, so 3 meter. It is already given to you. Okay. So then other values are, suppose load value and everything you will get, then this is the permissible your stress at compression and tension. These are, everything will be supplied, and theta and alpha is also known. So only unknown here are A1, A2, A3, and A4 and A4. Okay. So this is basically these are basically the variables. So means so other parameters. So I know basically. So only thing is that I have to calculate. So these are variables. So I have to calculate the value of A1, A2, A3, and A4. Okay. Now question is that his question is that without knowing A1, A2, A3, how you will calculate this constraint? Now basically, so you will apply some optimization methods here. So in every optimization method, so you have the initial solution. Suppose now you know that when you are applying Newton's method, or where you are applying steepest descent method or any other method, so you have to give an X naught. X naught is basically the initial solution. X naught is the initial solution, and from from there, I'm trying to find out the optimal solution. So x naught is basically, in this case, we have four variables, that is a1, a2, a3, and a4. So that means initially I have to define what is x naught, and for x naught I will calculate all these constraint and objective function value, and then I will apply this algorithm and I will try to find out I will try to find out the optimal value of a1, a2, a3, and a4. So I hope this is clear. So here a1, a2, a3, a4 are the variables. L is not variable, so L is user defined parameters. So I know what is L, what is P, what is theta value, what is alpha value, and all these permissible values are known, deflection values are known. So only unknown in this particular problem is the variables, that is a1, a2, a3, and a4, and basically, so I can apply. So in every optimization method, so you will have the constraint, you will have the objective function value, and basically, so you will start your optimization from a initial point. So in this case, suppose x naught is the initial point, and from x naught, so you calculate what is objective function value, what is constraint value, then you go to the next step. Okay, so you find out the next point basically, and then basically that way you just proceed, and you will get the optimal solution of the problem. So these two are the questions, and then I'm not assigning any value, but I have to give an initial value. So initial cross section you have to know. So in this case it is an initial cross section. So initial cross section value you can assign, that is initial solution, and from that initial solution optimization methods will find out the solution. So I hope this is clear. So these are some of the questions I have received, and then another question was this is again related to an LP problem. So here BI, I hope that question is about this one. So BI is 10 when its value is showing your positive 10. So it should be I'm telling it is negative 10. So basically it's a positive value, but if I write the last equation, so in that case what will happen, this minus f equal to 10 and f equal to minus 10. So that is basically I'm telling that f value is minus 10, but BI value is your positive, that is your positive your 10. Okay, so this is related to your LP problem, and I have applied simplex method here. So I think this was the problem. So here this is the maximization type problem, and I converted to minimization type problem by multiplying it -1, and this is the initial table, and here this is the minimum coefficient. So therefore I will select this particular variable x2, and then I have calculated the ratio, and this is the minimum ratio, and therefore this will be the pivoting element. So here I will make it 1, and others I will make it 0. Then basically, so in the next table, so this is, you can see that this is 1 and all of them are 0. And then you just see this is now the maximum negative value. So therefore x3 is the incoming variable. So x3 is incoming, so it will come to the basis, and then you calculate the ratio. So in this case, both are equal, that means 2 and 2. So I said that if there is a tie, both the value are equal. So in that case, I will consider the minimum 1. Okay, so you can consider any one basically. So minimum 1 you should consider, but as in this case both are equal, so you can consider any one. Okay. So in this case, I have considered the first one. So then this will be my pivoting element. And if I go for next table, so this is now 1 and this is 0, this is 0, 0, and I'm getting a solution, and there is no negative coefficient here. There is no negative coefficient. So in this case, this is minus f equal to 10 and f equal to minus 10. So this is my solution. Okay, so this is the solution, and alternately, what you can do, you can also consider this particular if you are considering that one, so but still solution is same. That means you are getting an alternate optimal solution. So here also this minus f equal to 10 and f equal to minus 10. Okay, so you are getting this particular solution. So I hope this is clear. So here b is 10. I think probably he is asking about this one, but your solution is minus 10. So this is all about today's your live session. But if you have any question, you can ask me and I will try to clarify that. Thank you. So is there any question? Okay, then as there is no question, so let us close this session here. So again, we'll interact in the next live session. So in the next part, we'll discuss about non-classical optimization methods, and that will be, there is any your queries, so that will be clarified in the next live session. Thank you.